Well, thanks, James, for finding me batteries and introducing me, and also Erica and the rest of the AstroTours team for having me. I'm very excited to talk to you about black holes. Um, yeah, so this is what you can expect to go through tonight. So first, I'm going to try to answer some of the questions you might have about black holes. And then I'm going to make you listen to the questions I have about black holes. And then we'll play a game if I don't yap too long. And then you can go look at the telescopes. I put a rain cloud because Google said it was going to rain yesterday, but I think it's clear today. So that should be a moon, I guess. Um, but what I really want you to do is leave today knowing that black holes are way more than just little dark balls that fly through space. They are so much cooler than that. Right. So I'll start with trying to answer some of the most common questions I hear about black holes. The first one being, what is a black hole? Okay, so you might think of a black hole as an extremely dense, compact astrophysical object. I did see something like that on the poll. Mathematically, I did see someone say this, which was pretty cool, a singularity. So there was a guy named Einstein, and he developed a theory of gravity called general relativity. And the way he thinks of gravity is that it's basically like curvature in space-time. So if you have like the heavier your object is, the more massive your object is, the more space curves around it. So you can see here for like a regular star, there's a little bit of a dent. And then as you go to more and more massive objects, that dent gets bigger and bigger. And when you go to a black hole, it's like infinitely curved. So it collapses to like a single point, which is what we call a singularity. So I saw someone say that, so that was cool. Yeah, so try to keep this idea of curvature in your mind. Astronomically, you can say a black hole is a dead star. I did see someone say that too, so that's cool. I put a little asterisk there because we might have other ways to describe black holes, which we'll get to soon. And finally, you might say that it's an object with really, really strong gravity, so strong that light can't even escape. So these are all valid ways to define black holes. There are actually different types of black holes. So in order from like least massive to most massive, there are primordial black holes, stellar mass black holes, intermediate mass black holes, and supermassive black holes. And we'll go through all of these one by one. So the first type I want to talk about are primordial black holes. I have to remember to talk at the microphone. So these are black holes that astronomers think may have come from the Big Bang. So you may have heard that at the very beginning of the universe, there were these really small over and under densities. And so you may have seen this picture before. This is the CMB, the cosmic microwave background, which is just showing that some regions in space were really dense and some were really not dense. And so we think that dense regions may have if they got too dense, they could have collapsed in on themselves and made like little baby black holes. That would be a primordial black hole. But the thing is that this is theoretical. We've never found one, but we think it could have happened. The next type of black hole is probably the one you're most familiar with, or like what you picture if someone says black hole. It's a stellar mass black hole. So this is the one that comes from a star dying. So basically, after a star is born, it can go through sort of two different evolutionary tracks. If it's a little star like our sun, as it gets older, it kind of expands and cools down, and then eventually the outer layers kind of just blow off, and you're left with the core of the star, and that's called a white dwarf. But if you're a really big star, you'll expand really, really, really big, and you'll actually, when you run out of fuel, you implode in what's called a supernova, and you can either become a neutron star, or if you're really massive, a black hole. So this is probably what most of you would think of if someone told you to picture a black hole. The next kind that probably comes to mind for you is a supermassive black hole. So these are basically like huge black holes at the centers of galaxies. And there are a few different ways we think they might be formed, but we don't know for sure. So one way is you just had like a really big star collapse and form like a huge black hole. Another possibility is two littler black holes merged to make a bigger black hole. And that just happened a lot of times. Or they could have formed through accretion. So accretion just means that the black hole is like eating the gas around it and growing. So these are some ways that we think that these could have formed, but we don't know for sure. This is an open question, which is exciting. And then the last kind is the intermediate mass black hole. So like it sounds like, it's basically in between the stellar mass black holes and the supermassive black holes, supermassive, sorry. And there are two places we think they might exist. So they might exist in the accretion disk of a supermassive black hole. So that just means like the gas disk around it. They might be found there. Another option is, like I told you, supermassive black holes are found at the centers of galaxies. There are these things called globular clusters, which are just collections of like millions and millions and millions of stars, but they're not big enough to be a galaxy. So they're like a baby wannabe galaxy. And we think at their centers, they might have an intermediate mass black hole. But these, oh, and the way we think that these form is probably just through stellar mass black holes merging to make bigger black holes. But this is also theoretical. We have never found one 100% for sure. But why it's weird is there are a lot. So this is basically saying like how many black holes we found versus mass. So we found a lot of stellar mass black holes and a lot of supermassive black holes. But there's nothing in the middle. And that's kind of weird. Like there should be something in the middle. So that's why we think they must exist, but we don't know where they are and why we can't find them. So that's another open question, which is also really cool. Another question that I've gotten a lot is why does it look like that? So there are a lot of features you might see on a black hole. So here are two pictures, artists' impressions of black holes. These aren't real. And now if we go back to our little game, can you try to point out anything where'd my mouse go? Well, I think you have the game open, but I must have to go this way. We did it. So just click on any features that you might see of interest to you. A lot of people are very interested in the things I'm going to talk about, so that's good. Wow, there's a lot of interest. Okay, cool. So I'm really happy because a lot of you are interested in this, and my friend told me that that probably wasn't interesting to you. So he's here. So I just want to say, oh my gosh, we went too far. I'm switching back and forth again. Okay, so where do I point? Okay, the first thing I think is interesting is that the black hole is black. So why is it black? So there's something called escape velocity. So if I like throw something in the air, it comes back down. And if I throw it faster, it goes higher, but still comes back down. But if I threw it fast enough, it would leave Earth, right? It would escape our gravity. And that's what escape velocity is. It's how fast something has to go to escape the gravitational pull of some object like the Earth. Earth's escape velocity is 11 kilometers per second-ish. And if you're going slower than that, you cannot leave the Earth. You will fall back down. So rockets have to go a lot faster than that. But for a black hole, its escape velocity is actually the speed of light. So light does have a speed. It's like 300,000 kilometers a second, which is way bigger than 11. And yeah, that's why they're black, because you have to go faster than light to escape. And so the region where it looks black, that's where light can escape from, and that's called the event horizon. So the next question, I saw a lot of people pointing at the disk, so that's exciting. What is that disk? So we call it an accretion disk. You're actually familiar with accretion disks because you've all heard of Saturn, I hope. And Saturn has these beautiful rings, right? That's why we love Saturn. That's an accretion disk. It's just a bunch of like dust and ice and rocks and stuff all orbiting around Saturn. So that's what a black hole has too, but its accretion disk is just gas, and that's how black holes grow, by eating that gas. So the disk is flat. And so I've been asked, like, how come it forms a disk and you don't just have gas falling all the way from every direction? That's a really good question. It's because the black hole is usually spinning, or the material around it is orbiting the black hole. And because of that, and because of something called angular momentum, as that gas orbits the black hole, any sort of up and down motions end up like canceling each other out, and the disk flattens out like a pancake. The disk is really, really hot, so it releases a lot of light, just like your stove glows. The accretion disk does that, but like way more. And that's how we see black holes, is through this accretion disk and other features that I'll talk about. So the disk is really interesting because it has a lot of dynamics that astronomers find cool, something like tidal disruption events. So what that is if a star or something gets really close to a supermassive black hole, if it gets too close, the gravity will actually rip it apart into something that looks like this, and that lets off a lot of light and energy, and we can see that with the telescopes. The next thing, this was probably one of the most clicked on parts. This little cylinder looking thing, that's called a jet. And so the way that these form is really, really interesting. It's one of my favorite things. So supermassive black holes, some of them will have magnetic fields around them, just like how the Earth has a magnetic field. The accretion disks around supermassive black holes can also have magnetic fields. And if you have the accretion disk and the gas is sort of falling into the black hole, it pulls the magnetic field lines in with the gas. And then there's this region really close to the black hole where anything in that region, including magnetic field lines, have to orbit with the black hole's spin. So the black hole is spinning, and then the field lines have to basically rotate with the black hole as it spins. That's called the ergosphere. And so as the black hole is spinning, and then the field lines are sort of twirling, it like winds them up to form a jet. And the jets can expel a lot of gas. They can be very bright, and they extend far beyond. So there's no scale on here, but this is a little galaxy. And then these are like sort of the lobes formed by the jet. So they're huge. Like you can see them way beyond the galaxy, and they impact the evolution within and outside the galaxy, which we'll also talk about a little bit. Another feature that I don't know if anyone clicked on, but you sort of have like another disk up here and down here. And so that's interesting. What that is basically, we talked about how you can describe gravity as curvature of space-time. So here is an example of the sun, and then it's sort of curved below here. And what happens is light will follow that curvature. It won't go straight like this. It will actually follow the curvature. So light from this star back here will curve around the sun and reach us here on Earth. And that happens with the black hole too. So here's a really helpful movie. You can see it's got that little disk above and below, but now if we like move the camera to be looking like bird's eye view, you can see that the disk, like this is just the back of the disk being bent around the black hole. Yeah. This was the thing that I really wanted to talk about, so I'm happy you want to hear about it. This side is brighter than this side. So what's going on with that? So you may have heard of something called the Doppler shift. What that means is if you hear like a siren or like a race car approaching you, it sounds like really high pitched, and then after it passes you, it sounds like really low pitched, right? Like that. I hope, sorry about that. So that's because the sound waves sort of get compressed as it's approaching you, and that raises the pitch. That makes it sound higher frequency. And when it leaves you, the waves are sort of spread out because the ambulance is moving. So that lowers the pitch and it sounds lower. That can happen with light too. So normally an object that emits light, like light will travel out in every single direction. But if that object is moving relativistically, which just means super fast, all of those light rays sort of get concentrated into one region like this, and that makes the object much brighter. So because the disk is rotating, so the side that's like coming at you is experiencing this, what we call beaming. It's basically a relativistic Doppler effect. So it experiences that beaming and it's much brighter, and the side rotating away from you is duller. Okay, this question, what happens if you fall into one? You should try not to. So in order for you to understand this, we have to talk about how tides work. So on Earth, There's high tide and low tide, which is when the ocean is like higher or lower. And the reason for that is because of the moon. So the moon orbits the Earth because Earth exerts a gravitational force on the moon, but the moon also exerts a gravitational force on the Earth. And that's what causes the tides. So basically, this point of Earth is closest to the moon, so its gravity is strongest. The closer you are to an object, the stronger its gravitational pull is. But this part on the Earth is a little bit further away, so it feels a little bit less gravity. And this part is further, so it feels the least gravity. And what this does, it kind of stretches the water out. And so the reason we have tides is because the Earth rotates through this little bulge that is made through that gravitational force stretching out the water, and we just rotate through the water. So that happens with a black hole too. So the part of you closest to the black hole feels way more pull than the part furthest away, and that stretches you out into spaghetti. And that sounds really painful, but what's actually really interesting is the bigger the black hole, the less stretched you'll get, because since it's like bigger, the ratio of the distance between your head and your feet is like smaller compared to if you had like a tiny black hole. Like that's a huge like proportion of the black hole's distance. So if you were going to fall into a black hole, choose a big one. And then if you had a friend that was watching you, it would look totally different. So for you, you would just pass through the black hole and like not even know that you passed the event horizon, but your friend would see something else. So they would see you fall into the black hole, but the closer you get, the slower you move, and also the redder you become. You turn red, and then eventually you'd go into even things like infrared, like the light that I'm using to change slides right now. So this is complicated, and I'm just going to say it comes from Einstein. Okay, so how do we study black holes? At the beginning, I told you that there were two theoretical types of black holes that I don't actually know if they're real, and there are two real types. And how do we study those real ones? So there are a few ways. The first and easiest way is just there's stuff around the black holes, and we can look at that. So at the center of our galaxy, we have a supermassive black hole. It's called Sagittarius A star because it's like towards the constellation of Sagittarius. And this is data collected over like decades of the stars orbiting the galactic center. So we know there's something there, but we can't see anything because the black hole is black. So, but they're going around something. So that tells us there must be a black hole there. Another way we can find them is sometimes they'll have what we call a companion star. So that's just like a star that's near the black hole that kind of like it gets its gas sucked off by the black hole and then it falls into the black hole like this. And this releases a lot of light. So we can find that with telescopes. Another way is these tidal disruption events that I talked about. So if a star gets too close to the black hole and is fully ripped apart, that lets off a ton of light, and we can find that with telescopes. Also, sometimes the disk around the black hole, this accretion disk, flares. So you can see that it kind of gets brighter for like half a second there. There are a few different things that could be causing it. It could be something like this, or it could be something to do with like the magnetic field lines, but we can see light from the disk and sometimes it gets bright. So this here, how the stars orbit the galactic center, you can actually calculate the mass of our black hole from those orbits. So now I want you to guess how massive our black hole is. So this is, oh my God, we fixed the mic. Thank you. I just want to say quick that this is not like 0 to 10. This is, oh my, hello? Oh, this is, thank you, Erica. Erica saved the day. So these numbers here are actually the number of zeros. We call this a log scale. So the 4 would be like a 1 with 4 zeros, so like 10,000 times the mass of the sun. Or like the 6 would be like 1,000,000 times the mass of the sun. So take your guesses. A lot of you are choosing around 8 or 9, so you think it's 1,000,000,000 times heavier than our sun? Wow, we have a lot of peaks. I think it's stabilizing. I appreciate all the hearts. That's so cute. I didn't know it could do that. Wow. Okay. So I don't know. There is a right answer. Will it tell you? It's not. It's not quiz time. It's not. We're not there. Sorry. It's 6. So it's 4.5 million times the mass of our sun. So like a third of you got it. That's cool. Right. I went too far. Okay. So another way that we can find black holes is through something called gravitational waves. So there was a guy named Utkarsh who gave a talk, I think 2 months ago, and he talked a lot about this. That's Utkarsh, if you don't remember him. And we actually have a group here at U of T that study these gravitational waves, and this is them, and they have a dog. My group doesn't have a dog, but they do. So yeah, this is a little video demonstrating what gravitational waves are. Oh, I don't have to talk into that microphone anymore. That's so nice. Play, 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 play. Oh my gosh. Play, play. Well, what's supposed to happen is that these two little balls are black holes, and then they orbit each other, and then they get closer and closer and closer because they're going to merge. And the closer they get, like they send out these little ripples, and these ripples get bigger. And that's what's supposed to happen. You can Google it. It's sorry. And then I think I'm over time because I messed up with the whole microphone thing, so I'm gonna skip this slide. But that's one way we can find them. Basically, when they merge together, they send out these ripples through space-time, and then we can measure those ripples on Earth with some really smart technology. Another way to find them is through the Event Horizon Telescope. So this is, you've probably seen these. I think this is like the most looked at picture in the world or something. Maybe till Taylor Swift got engaged. But so this is a picture of a black hole that actually is 1 billion times more massive than our sun. And then this is our black hole. And these pictures were taken by basically taking a ton of telescopes all over the Earth. And so if you have a bigger telescope, you can see further away and you can see tinier things. Does that make sense? So if you take a bunch of telescopes all over the world and you like add them together, it's basically like making a telescope as big as the world. And with that, you can see really tiny things. So Sagittarius A star, our black hole, he is big, but he's far. So he looks tiny to us. So yeah, that's another way. You can just take a picture of one. And finally, you can run simulations. So this is more what I do. So this is my supervisor, Bart. He does have a dog. He just doesn't bring it to work. But so this is a black hole, and then this here is that disk that I showed you before, but now you're looking on the side, and it's like way fatter than it looks when artists draw it. And then these little squiggles like coming into the black hole, that's how the black hole is accreting that gas. And then this is a video from Braden, who is a grad student here, and now you're looking like down on the black hole. And this is the disk like swirling in to the black hole. So yeah, we can run these simulations to try to understand like what sort of physics is happening around there to help us try and explain what we see with the telescopes. And then my favorite part, why do we care about black holes? So as astronomers, black holes are really, really cool, like just in general, because you don't know what's in them, but also because you can just learn so much physics from them. So one thing is that they are basically tests of gravity. So when the first gravitational wave was detected in like 2015 or something, it was like huge news. I remember where I was. I was in my room studying for calculus. And it was huge news. And everyone's like, oh my God, we proved Einstein right, because Einstein's theory of gravity predicts that these gravitational waves are things that happen. And we saw them like this. This is an example of a gravitational wave. And the other thing that Einstein predicted was this light bending that I showed you before, that the light bends around the black hole. And we see that. So Einstein was double right. Another thing, I just put this here to freak you out. But they're just really cool if you like math. Like you can write down what they are with math. Isn't that crazy? That's cool. And they also push the limits of instrumentation. So this is a picture of something called the LIGO detector. This is the really big telescope that detects gravitational waves. So it's huge, and it's really cool how it works. And that's the slide I skipped, sorry. And this is, again, an image of EHT. So we're really pushing, instrumentation means like how you build the telescopes. Sorry, I should have said that. Our telescopes are really cool to find these black holes. Another thing is they really impact galaxy evolution. So I told you that we have supermassive black holes at the centers of galaxies, like pretty much every single galaxy. But they kind of affect what's going on around them because, like I said, they have these jets, and these jets do wonky stuff. So one thing is that stars exist in galaxies, of course. So all of these little bright pink spots are places where stars are being born. But the thing is, in order for a star to be born, it needs to be really, really cold, like minus 270 degrees. And these jets from the black hole, they heat up the gas. And then the gas gets so hot that you can't make stars anymore. So your galaxy kind of dies. And another thing that they do is they let out these winds. Thanks. And those winds basically blow out all of the different like elements that exist inside the galaxy. So now you're basically depositing any sort of, elements that you made inside. You're like letting them go out into the rest of the universe. And they also have magnetic fields, and those magnetic fields also do things outside of the galaxy. So they affect how the galaxy itself evolves and the gas connecting galaxies. And then the reason I think they're really cool is because they're just a really extreme environment that you can't get here on Earth. So they're like a little lab in space. So this is another simulation from my supervisor, and there's just a lot happening here. Basically, the gas around a black hole is really, really hot, has a really, really large magnetic field, and very high energy particles that are doing really cool things that you can't get on Earth. So that kind of brings me into my research. So hopefully you like that. So in order to simulate, so basically like make a black hole in my computer, there are a lot of different things happening. So I told you that they basically expand to like beyond the distance of a galaxy, right? But there are more interesting things happening on smaller scales. So like the accretion disk itself is super interesting, and the things the particles are doing inside the accretion disk is super interesting. But in order to simulate all of these different scales, you need different kinds of simulations. So to do this part here, where you're looking at like the jet and how it extends beyond the galaxy, you need these things called cosmological simulations, which are essentially universes in a box. Like you have a ton of galaxies and you like watch from like the Big Bang and how they evolve. And the thing is, since this is such a large scale, like every time you go to smaller levels, you have more information. Does that make sense? Like you have more physics there. And every time you zoom out, you're losing information. You're, oh my gosh, losing, you're losing physics. So these guys have really bad physics. The next sort of interesting scale is this accretion disk. So it has more physics than here, but not all of the right information. And so here you're modeling that gas that's falling into the black hole as a fluid. So like fluids are things that flow like water and stuff. So that's how you're modeling the gas if you want to do like an accretion disk, like what I just showed you, my coworker does. But what's happening inside of the disk is all of these little gas molecules, particles, I should say, are moving around and doing interesting stuff. And if you want to get this, then you need to run something called a particle simulation, where you're actually modeling what each particle is doing. And so the thing is, this is 100 billion times bigger than this. That's like a lot. And so if you wanted to model what the particles are doing on this scale, like your computer couldn't do it, and supercomputers can't do it. So that's why you have to sort of lose information. So what I'm trying to do is add information from these kinds of simulations into these simulations and like bridge the gap between them. That's what I'm trying to do. So the specific problem I work on, So the black hole has the accretion disk, and then around the accretion disk, there's this sort of layer of really hot gas called the corona. You may have heard of the corona because last year there was an eclipse. This is a picture my friend took of the eclipse where you can see the solar corona. So it also is just really hot gas that exists around the sun. But the thing is that this hot gas lets out a lot of light that we can see with our telescopes. So one thing that we think is sort of causing this light to be released is something called magnetic reconnection, which is a really cool thing. So basically, I said that the accretion disks can have magnetic field lines. And what happens if those field lines get all twisted up, they can like break off and like shoot gas out the sides. So that's what's happening here. The field lines are breaking right here and then shooting stuff out. And so this happens on the sun. It's what causes the auroras here on Earth. So this bright thing here, that's the reconnecting. And then that thing it shot off, that's called a coronal mass ejection. That's basically the gas being shot out over here. And so we think that this is what could be powering the corona. And so how this might look on an accretion disk, we might have some of these loops like you just saw in this sun movie. We might have, well, some of those loops on the disk itself. And so this is another friend I have here. Her name is Jibwa, and she runs those simulations of the accretion disk, the ones with a little bit less information. And so it's hard to see, but there's a black hole right here. My hand is shaking, but it's there. And then here, this is the accretion disk. It's blue because it's colder. And then here's the jet. It's red because it's hotter. And then all of these little black lines, they probably look like dots to you, but they are lines. Those are the magnetic field lines. So if you zoom in on this region here, outlined in blue, you get something like this. So now this is the black hole. I know it's white, I'm sorry, but this is the black hole. And then this red hot region is the corona. And if you zoom in on that, it looks like this. And so you can kind of see that you have the lines here connecting and pinching off and like letting out big chunks of gas here. Sort of looks like this. So that's what I'm simulating. I'm basically simulating this region to try to get more information to put into these simulations. So the information I'm trying to add is how that light is being produced. Like I said, it probably comes from reconnection. So in physics, we call light radiation. And if something is radiating, it's losing energy. And you can also say it's cooling. If you're losing energy, you're like getting colder, your temperature's going lower. So in order to simulate that, I want to tell the simulation to lose energy where it's hot, which is basically right here, where that, can I hit play again on the movie? So like where we saw that this here, this bright thing, it's really, really hot there. So I wanted to lose energy there. But I also wanted to lose energy where things are moving fast, which is basically that huge gas blob that got shot out into space. So I want to take energy away here and here, and I need to tell the simulation with less information how to do that. And so here are my own simulations. So this is the little box I'm simulating again. This here is showing you where it's hot. The red stuff is hot. And then this here is showing you where I'm taking energy away. So, yeah. And then the other thing I said, I want to take energy away where it's fast. So that's happening here. So this is showing the speed. So red means it's going this way, blue is going that way. And then here is where I'm taking away energy where it's fast. So I am actually able to get a little bit more information now into those simulations that don't have the full picture. So the reason I'm doing that is, like I said, if I take the model that I've produced and I add that missing information back into a simulation of an accretion disk, then it can help us explain what we actually see in the sky with telescopes. So to summarize, black holes, they are mysterious, but it's just, that just makes them really exciting. They have very strong gravity, and we can't directly study them, so we have different ways to study them. We found ways to observe them with telescopes or gravitational waves or by looking at the stuff around them. But the main thing is that there's just so much to do with them. There's so much physics happening with them, different kinds of physics, exciting things you can do with them. So yeah, I hope you took that away. And now we can do the quiz. James said I had 3 minutes. So we can do it. One question per minute. Okay. So, okay, are you ready? Okay. Oh my gosh, you guys are ready. Okay, I think it's stabilizing. We're good. Oh my God, where's question one? Oh, you can see the questions already. Okay, go ahead. I haven't been on your side. Can you not see it?
I think you have to press enter to.
That's, oh my gosh, now can you see it? Thank you. This has not been a good day for tech. You guys are quick. All my students that I TA in here, I want you to take note of how fast these guys are. Okay, I think it's not going up anymore. Yeah. Okay. I don't know how to close it. Do I hit enter again? Does it work? Do I just hit next? Okay, the next question. You can see the question again, I hope. What happens if you fall into a black hole? So I didn't list the options last time, sorry, but you turn into pasta, you get stretched apart, or you turn blue. Everyone answered. That's great. Okay. Oh, did it show? Yeah, B was right. That was, you get stretched apart. I'm glad no one said blue. Okay. What type of black hole have we taken a picture of? This one's trickier. You have to connect things I said. So supermassive, intermediate mass, or primordial. That one you have to think. You can talk with your friends. You did it. Will it show me? Oh my gosh, you did it! It is the supermassive one. We took a picture of the black hole at the center of our galaxy. That is supermassive Sagittarius. Woo! Um, I don't have prizes, but you can feel smart. So that's cool. Apollo. Great stuff. I also love goats, so nice. Okay, that's it. Thank you so much. Yeah, you're right. Oh my gosh. Now we're back on this one.
All right. Thank you for that wonderful talk. We do have some time for questions before people head out. So any questions in the room? Start right here at the front.
Two.
Sure, go for it.
Okay, first one was, you said that we haven't found any black holes. If we found a black hole, how would we be able to tell if it's primordial?
Okay. The question was that I said we haven't found primordial black holes, and if we found one, how would I know it was primordial and not just like a stellar mass black hole? That's, well, I think maybe the size, like when a stellar mass black hole is made, like there's a certain size star that has to exist to make it. Does that make sense? So I guess if it's too tiny, we could think it was, but this is more a question for cosmologists than me. But that's a good question. And your second question. If it was intermediate, it could. If it was intermediate mass, that wouldn't necessarily mean it's primordial. It would just mean, so intermediate mass black holes probably come from two stellar mass black holes merging. And we just haven't found them yet, but they must be there.
Second question was, how do black holes have magnetic fields?
That's such a good question. Okay, thank you. Black holes don't have magnetic fields themselves. There's something called the no-hair theorem, which sounds kind of crude, and I think it's supposed to. But basically, it says black holes aren't allowed to have anything other than mass, spin, which is like how fast it's, or charge, like an electron has a charge. It's not allowed to have a magnetic field. So it's not the black hole itself that has a magnetic field, it's that the gas in the accretion disk has a magnetic field, which is happening because there are charged particles moving in the gas. That helps? Okay, thanks.
Let's go right here.
It might be a little bit futuristic question, but do you have any predictions for what might happen if the Andromeda galaxy collides with ours? Because I know they like our galaxy has a black hole, and then that galaxy has a black hole. So what do you think might happen?
That's a fun question. So the question was, what happens if Andromeda, which is our nearest galaxy, like 250 million light years away, it's eventually going to collide with us. So what happens then? What will happen to the black holes? So basically we'll be dead by then. But yeah. So actually when galaxies merge, it's a very violent but pretty process. And usually we think that the black holes in the centers themselves would also merge, but it would take a long time, but it would happen. And then you get a big one. Yeah.
Let's go over there.
How eventually just being stuck into that holes? Is this our fate? Or everything we just stuck in the hole?
That's a good question too. So the question was, is it our fate to be sucked into a black hole? The answer is that you have to be close enough to the black hole to be sucked in. Like if you're just chilling, you're not going to get sucked in. Like if I was like an astronaut in space near the Earth, I wouldn't get sucked into the Earth. I'm stuck on the Earth right now because I'm close enough for the gravity to catch me. But you have to be close enough to the black hole for its gravity to catch you. So if you're just chilling, you're okay. Just don't go near one.
Let's go over there.
People's excited kind of retreat, but what about like I'm thinking about like cosmic radiation? We like once afterwards with the billions and billions of years, did you ever like did this delve into the black hole with that information?
That's a really complicated question. Very good. So the question was, there's something called Hawking radiation, which says that technically particles can spontaneously just like appear, which is possible in physics. And so we think that near like the edges of black holes, if particles just appear, like maybe they can get out of the black hole. So the question was like, this is how black holes like radiate, like they lose mass this way, and eventually they should technically fully evaporate and not exist anymore. But the time scale for that is longer than the age of the universe. Like it's so long. And so we were asking if you could get the information that went into the black hole back out. So this is way beyond what I know, but there are theories about like the information that is lost in a black hole, like if it's just imprinted on the surface of a black hole. And I don't really know the answer to that. You have to go down a YouTube rabbit hole for people who think they know the answer. But this is all Stephen Hawking, really smart stuff. I don't know the answer if you can get what comes in back out, but people think about it, but it's not solved from my understanding. Thank you, though.
Let's go right here.
So, the first picture, MN7 and Categories A. So the vision of the accretion disk, is that the result of the collections of data that's on radio astronomy, or is it more on the infrared slash the visible spectrum?
Yeah, so the question was the pictures I showed you of the two black holes, if that's taken in radio or infrared, which is two different wavelengths of light that describe like how energetic the light is. Those were radio pictures, I'm pretty sure. So I think it was like 230 gigahertz. That's the wavelength they looked at. Frequency, I should say. Yeah, that was radio. James chooses.
Let's go right here.
Hi, so I just wanted to ask, there was at some point an article that I read about the possibility of two neutron stars colliding to form a black hole. And I want to ask whether or not there's any confirmation of that being possible or having happened, or whether or not, if not, theoretically, that is something that could be a formation total.
Yeah, so okay, sorry, the question was, if two neutron stars collide, do they make black holes? Like, that's theoretically a thing. Is it confirmed? So, basically, you get a black hole if you just put too much matter in one spot. So if you collide two neutron stars, you will have too much matter in one spot, and you will get a black hole. That's the theory behind it. And we have one kilonova that we found. Was it two? One for sure. The very first thing that this gravitational wave detector found was two neutron stars merging, which is called a kilonova. And if it left behind a black hole, I don't know if there's a way we could see that, but it should. I'm not sure if we can have confirmed it or not with observations.